Welcome! In this video, we will explore our work on robust snapshot radio SLAM by Ossi, Kaltiokallio et al., recently published in IEEE Transactions on Vehicular Technology. This research tackles the challenges of integrating simultaneous localization mapping, or SLAM, into 5G and 6G systems. My name is Henk Wymeersch, and I'm with Chalmers University of Technology. Let's dive in. SLAM has gained significant attention in the context of millimeter wave signals for 5G and 6G. These systems leverage both line-of-sight and non-line-of-sight propagation paths to simultaneously localize the user and map the surrounding environment. This in turn reduces the requirements in terms of infrastructure, such as synchronized base stations. However, a major challenge arises due to higher order non-line-of-sight paths, which can degrade localization performance. Traditional approaches either identify and discard these higher order non-line-of-sight paths or attempt to utilize them, but both methods have limitations. Our goal is to solve the SLAM problem in mixed line-of-sight and non-line-of-sight conditions by robustly identifying and discarding multi-bound signals. Our method focuses on geometric consistency to identify line-of-sight and single-bound non-line-of-sight paths, separating them from clutter and higher order non-line-of-sight paths. Here is the key insight. We use a minimal subset of propagation paths to establish a reliable localization solution. For example, two paths are sufficient in line-of-sight conditions, namely the line-of-sight path and one single-bound non-line-of-sight path. In non-line-of-sight conditions, where the line-of-sight is blocked, we need four single-bound non-line-of-sight paths. By solving the problem with these minimal subsets and checking the consistency with all remaining paths, we can ensure robustness against outliers. This approach allows us to address the SLAM problem effectively, even in environments with mixed propagation conditions and measurement outliers. Let's consider an example where the line-of-sight is present. There are 6 paths in total, line-of-sight and 5 non-line-of-sight paths. But we do not know which ones of these 5 are the single bounce paths. So there are 5 possible minimal subsets. Let's pick the line-of-sight path and the first non-line-of-sight path to compute a solution, say x0. We then check all the paths in terms of how consistent they are with this solution, based on a suitable cost function. From this, we can find a set of outliers and inliers. For instance, paths number 4 and 5 have a high cost and are considered outliers, so they're not consistent with the solution x0. The paths 0, 1, 2, and 3 are consistent and have a lower cost. From the inlier set, we compute a new solution with a corresponding cost. This is shown in the last column. We repeat this process for each of the 5 minimal subsets. In this case, with the 5th non-line-of-sight path, we see that the initial solution x0 is in the wrong location. This leads to a high consistency cost with most of the other paths. Overall, we can conclude that paths 1, 2, and 3 are single-bound non-line-of-sight paths, and we discard paths number 4 and 5. To validate our algorithm, we conducted experiments using a stationary base station and a quasi-stationary user equipment. Both devices were equipped with millimeter wave capabilities, allowing for electrical beamforming and beam sweeping. Measurements were taken across 45 positions, of which 32 were in line of sight and 13 in non-line of sight. Of the total of 362 detected propagation paths, 104 were classified as outliers by our algorithm. These results will provide a robust experimental foundation for our method and demonstrate the practical applicability. The figure on the left shows an example location without line of sight. The single bounce interactions are shown in orange, while the higher order interactions are shown in purple dashed lines. The figure on the right shows the positioning performance with the black line, which nearly coincides with the blue ground truth. The red crosses show the landmarks obtained from the first order interactions detected by our algorithm. You can see that these match well with the map. Note that this map was not used as prior information in the proposed methods. In terms of quantitative performance, the proposed method provides sub-meter accuracy in both line-of-sight and non-line-of-sight conditions. The method can also determine the user orientation within around 2 degrees uncertainty and provide nanosecond level clock synchronization. We also observe that the method is much slower for the non-line of sight condition since larger minimal subsets need to be used. In summary, we have developed a snapshot SLAM algorithm that is robust to outliers, capable of identifying and discarding multi-bounce propagation paths based on spatial consistency. This method can function as a standalone solution or be integrated with filtering techniques. Furthermore, it opens the door to potentially leveraging multi-bounce paths to improve SLAM performance. For more details, check out the publication linked on the right. This concludes our presentation on robust snapshot radio SLAM. If you have any questions or would like to explore our datasets, please reach out. Don't forget to like and subscribe for more content on cutting-edge wireless research. See you next time, and thank you for watching.